So here's something worth thinking about as you settle in tonight. Right now, right this very second, the ground beneath you is moving. Not in some dramatic, catastrophic way. Nothing you'd notice, but it's moving. The continent you're lying on is drifting, creeping along at roughly the speed your fingernails grow. A few centimeters a year. That's it. And yet that tiny, almost absurdly slow motion is responsible for some of the most powerful events this planet has ever produced. We're talking about forces that can level entire cities in under a minute. Forces that can reshape coastlines, redirect rivers, lift mountain ranges thousands of feet into the sky over millions of years. All of it starts with that quiet, imperceptible drift happening right now, right beneath you. And I think that's what makes earthquakes so fascinating, honestly. They sit at this strange intersection of the incredibly slow and the terrifyingly fast. Tectonic plates spend decades, centuries, sometimes thousands of years building up stress, just grinding against each other, millimeter by millimeter. And then all of that accumulated energy releases in a burst that might last 10 seconds, maybe 30, rarely more than a few minutes. It's like the earth has been holding its breath, and then it exhales all at once. So tonight, let's talk about how all of that works. Not in a rushed, textbook kind of way, but slowly, piece by piece, the way you'd actually want to hear it explained if you were just lying here, curious and comfortable, letting the ideas wash over you. Let's start at the very beginning. And I mean the real beginning, before anyone understood plate tectonics, before anyone had even the faintest idea why the ground shook. Because for most of human history, earthquakes were a complete mystery. They were terrifying, unpredictable, and seemingly random. And when something that powerful defies explanation, people reach for the stories they have. The ancient Greeks had a few ideas. Thales of Miletus, who lived around 600 BCE, thought the earth floated on water, like a giant raft, and that earthquakes happened when waves in that cosmic ocean rocked the land. It's a beautiful image, actually. This whole planet just bobbing on an infinite sea. Not correct, obviously, but you can see the logic. He was trying to find a natural explanation, which was pretty radical for his time. Most cultures attributed earthquakes to gods or supernatural creatures. In Japanese mythology, there was Namazu, a giant catfish that lived beneath the islands and thrashed around when the god Kashima wasn't keeping it pinned down with a massive stone. Hindu mythology described the earth as being held up by elephants standing on the back of a turtle, and when any of them shifted, the ground trembled. The Maori people of New Zealand told of the god Ruaumoko, trapped beneath his mother the earth, whose struggles caused the shaking. And here's the thing. These aren't just quaint old stories. They tell you something important about how universal the experience of earthquakes is. Every culture that lived in a seismically active region developed an explanation because they had to. The ground is supposed to be the one thing you can count on. It's supposed to be solid, stable, the foundation of everything. When it betrays that trust, you need a reason why. Aristotle had his own theory, and it was actually pretty influential for a very long time. He proposed that earthquakes were caused by winds trapped inside underground caverns. These winds, he thought, would rush around trying to escape, and the shaking you felt at the surface was the result of all that subterranean turbulence. He wrote about this around 340 BCE in his work Meteorologica, and his ideas dominated Western thinking about earthquakes for nearly 2,000 years. 2,000 years. That's how long it took before anyone came up with something substantially better. And the reason Aristotle's theory stuck around so long is that it wasn't entirely unreasonable. People did notice that earthquakes sometimes seemed to correlate with weather patterns, or that strange sounds or gases would emerge from the ground before or after a quake. So the idea of underground wind had a certain plausibility to it, even if it was fundamentally wrong. The real shift in understanding didn't start until much, much later, and it began, as so many things in science do, with a disaster. November 1st, 1755. Lisbon, Portugal. It was a Saturday, All Saints' Day actually, and the churches were full. Around 9:40 in the morning, the ground began to shake. The first shock lasted somewhere between 3 and 6 minutes, which is an extraordinarily long time for an earthquake. Think about that. Close your eyes and count to 60. Now imagine the floor beneath you lurching and rolling for 3 to 6 times that long. The great churches and palaces of Lisbon, built of heavy stone, began to collapse. And then, maybe 40 minutes later, a second major shock hit. And then a third. But the shaking was only the beginning. The earthquake had originated somewhere in the Atlantic Ocean, probably along a fault zone southwest of Portugal, and it generated a massive tsunami. Waves between 15 and 20 feet high surged up the Tagus River and flooded the lower parts of the city. And as if that weren't enough, fires broke out across Lisbon. All those candles lit for All Saints' Day, knocked over in the shaking, and burned for nearly 5 days. By the time it was over, somewhere between 30,000 and 60,000 people were dead. Some estimates go even higher. Much of one of Europe's wealthiest and most powerful cities was simply gone. Now, the Lisbon earthquake is important not just because of its scale, but because of what it did to European intellectual life. This was the Enlightenment. People were actively questioning old assumptions about the natural world, about God, about the relationship between the two. And here was this catastrophe that struck on a holy day, that destroyed churches full of worshippers while leaving the red light district relatively intact. Voltaire wrote about it. Kant wrote about it. Immanuel Kant, the philosopher, actually wrote 3 separate essays on the Lisbon earthquake, and they're among the earliest attempts to study earthquakes scientifically. He proposed that earthquakes were caused by the collapse of underground caverns, which wasn't right either, but he was asking the right kinds of questions. He was trying to find patterns. He gathered reports from across Europe about when and where the shaking was felt, trying to map the extent of the event. That impulse, to collect data, to look for spatial patterns, to treat an earthquake as a natural phenomenon that could be studied rather than a divine punishment to be endured, that was genuinely new. But understanding earthquakes requires understanding the earth itself, and in the 1750s, nobody really knew what the earth was made of or how it was structured. The interior of the planet was as mysterious as the bottom of the ocean. More mysterious, actually, because at least you could drop a weighted line into the ocean and measure depth. You couldn't do anything like that with the Earth's interior. So for the next century and a half, progress was slow. People documented earthquakes more carefully. They started building instruments to detect ground motion, the earliest seismoscopes, some of them remarkably ingenious. There's a famous one attributed to the Chinese polymath Zhang Heng, who supposedly built a device around 132 CE, way back in the Han Dynasty, that could detect distant earthquakes and indicate their direction. It was a bronze vessel with 8 dragon heads around the outside, each holding a bronze ball in its mouth, and when the ground shook, an internal mechanism would cause one of the balls to drop into the open mouth of a bronze toad sitting below, indicating the direction the seismic waves had come from. Whether it actually worked as described is debated. We don't have the original device, only historical accounts. But the concept is remarkable. The idea that you could build a machine to sense something happening hundreds of miles away in the 2nd century is just extraordinary. In Europe, serious seismology didn't really get going until the 1800s. Robert Mallet, an Irish engineer, is sometimes called the father of seismology, and he earned that title through sheer determination. After a major earthquake struck the Basilicata region of southern Italy in December 1857, Mallet traveled there personally to survey the damage. And what he did was genuinely innovative. He systematically cataloged the destruction, noting which direction buildings had fallen, how walls had cracked, which structures survived and which didn't. From all of this physical evidence, he worked backward to determine the direction and origin point of the seismic waves. He was essentially doing forensic engineering on an entire landscape. He coined the term seismology itself, and he created some of the first maps showing the intensity of shaking radiating outward from a central point, which he called the epicenter. That word, epicenter, that's Mallet's contribution to the language. But here's what Mallet and everyone else in the 19th century still couldn't answer. Why? Why did earthquakes happen where they did? Why were some regions constantly shaking while others seemed perfectly stable? If you looked at a map of earthquake locations, there were obvious patterns. They clustered along certain belts, particularly around the edges of the Pacific Ocean and through the Mediterranean and into Central Asia. But nobody could explain why those patterns existed. The data was there, staring everyone in the face, but the theoretical framework to make sense of it hadn't been invented yet. And that brings us to one of the most remarkable, and honestly, one of the saddest, stories in the history of science. Because the person who first proposed the correct answer was almost completely ignored during his lifetime. His name was Alfred Wegener, and he was not a geologist. He was a German meteorologist and polar explorer, a man who spent his career studying the atmosphere, not the ground beneath it. But in 1912, Wegener presented a theory that would eventually revolutionize our understanding of the Earth. He called it continental drift. The idea, at its core, was simple and audacious. Wegener proposed that the continents had not always been in their current positions, that they had once been joined together in a single supercontinent. He called it Pangaea, from the Greek for all Earth, and that over millions of years, they had slowly drifted apart to their present locations. He pointed to evidence that, in retrospect, seems almost embarrassingly obvious. The coastlines of South America and Africa fit together like puzzle pieces. Identical fossils of the same ancient plants and animals were found on continents separated by thousands of miles of ocean. The same fern, Glossopteris, appearing in South America, Africa, India, Antarctica, and Australia. The same small reptile, Mesosaurus, found only in Brazil and South Africa. Geological formations, specific types and ages of rock, matched up across ocean basins when you mentally pushed the continents back together. Wegener laid all of this out in his 1915 book, The Origin of Continents and Oceans, and the geological establishment basically laughed at him. Not entirely without reason, Wegener had a serious problem. He could show that the continents had moved, but he couldn't explain how. What force could possibly push entire continents across the surface of the Earth? Wegener suggested that the continents plowed through the ocean floor like ships through ice, driven by centrifugal force from the Earth's rotation and tidal forces from the Moon. And geophysicists quickly showed that those forces were far, far too weak. The math didn't work. The mechanism was wrong. And because the mechanism was wrong, most scientists felt justified in dismissing the entire theory, evidence and all. It's a pattern you see again and again in science, a correct observation rejected because the proposed explanation is flawed. And it's worth sitting with that for a moment, because Wegener spent the rest of his life defending his theory against often vicious criticism. He was called a dreamer, an amateur meddling in fields he didn't understand. The president of the American Philosophical Society called his theory utter damned rot. And Wegener never got to see himself vindicated. In November 1930, he died on an expedition to Greenland, trying to resupply a remote weather station on the ice cap. He was 50 years old. His body wasn't found until the following spring, buried under the snow. And his theory of continental drift remained on the fringes of science for another 3 decades after his death, waiting for someone to figure out the one thing Wegener couldn't: the mechanism, the engine that drives the continents. The reason the Earth's surface is alive and restless and capable of producing the very earthquakes we're here to understand tonight. And that engine, when it was finally discovered, turned out to be hiding at the bottom of the ocean, in a place no human being had ever seen: the mid-ocean ridge, a mountain range longer than anything on land, winding through the darkness of the deep sea, like a seam stitched across the planet. Now, to understand how this discovery happened, you have to remember that for most of human history, the ocean floor was a complete mystery. People knew the oceans were deep, but they had no real picture of what the bottom looked like. Was it flat? Was it muddy and featureless? For centuries, the assumption was basically yes. The seafloor was imagined as a vast, boring plain, like a flooded desert. And honestly, why would anyone think otherwise? Nobody could see it. The deepest parts of the ocean are under miles of water, in total darkness, under pressures that would crush a human body like a paper cup. It was, in a very real sense, less explored than the surface of the moon. But then came the wars. And here's one of those strange threads in the history of science. So much of what we know about the Earth came from military technology. During World War I and especially World War II, navies needed to understand the ocean. They needed to detect submarines. They needed to map the sea floor for laying cables and navigating safely. And so they developed sonar, sound navigation and ranging, which works by sending pulses of sound down into the water and listening for the echo that bounces back from the bottom. By timing that echo, you can figure out how deep the water is at any given point. Do that thousands and thousands of times along a ship's path, and you start to build a picture. And the picture that emerged was astonishing. The ocean floor wasn't flat at all. It had trenches deeper than any mountain is tall, the Mariana Trench, for instance, plunging nearly 7 miles below the surface. It had vast abyssal plains, yes, but it also had something nobody expected: an enormous mountain range running right down the middle of the Atlantic Ocean, roughly parallel to the coastlines on either side. This is the Mid-Atlantic Ridge, and when scientists started mapping it in detail in the late 1940s and 1950s, they realized it wasn't just an Atlantic thing. It connected to similar ridges in the Indian Ocean, the Pacific, the Southern Ocean. It was a single continuous system of underwater mountains stretching over 40,000 miles around the planet. 40,000 miles. That's longer than the Earth's circumference at the equator. It's the longest mountain range in the world, and almost all of it is hidden underwater. Now, one of the key figures in mapping this was a woman named Marie Tharp, and her story is one of those that deserves more space than it usually gets. Tharp was a geologist and cartographer working at Columbia University's Lamont Geological Observatory in the 1950s, alongside her colleague, Bruce Heezen. At the time, women weren't allowed on research ships. That was just the rule, absurd as it sounds. So Tharp couldn't go collect data herself. Instead, she stayed on land and painstakingly plotted the sonar readings that Heezen and others brought back from their expeditions. She took those thousands of depth measurements and turned them into detailed cross-sectional profiles of the ocean floor, building up a picture of what the Atlantic seafloor actually looked like. And here's where it gets really interesting. As Tharp drew her profiles of the mid-Atlantic ridge, she noticed something peculiar. Right along the crest of the ridge, running along its very spine, there was a deep valley, a rift, a gap. It looked like the ridge was being pulled apart from the center, and Tharp immediately recognized what this might mean. If the seafloor was splitting open along that rift, then maybe new material was welling up from below to fill the gap. Maybe the ocean floor was growing, spreading outward from the ridge like two conveyor belts moving in opposite directions. When she brought this to Heezen, he dismissed it. He called it girl talk. That's a direct quote. Because what Tharp was describing sounded an awful lot like continental drift, and in the early 1950s, continental drift was still considered fringe science, remember? It was Wegener's discredited idea. No serious geologist wanted to be associated with it. But Tharp was persistent, and she was meticulous, and the data kept supporting her. That rift valley was real. It was consistent. It showed up in profile after profile. And eventually, Heezen came around, especially after he noticed that the locations of earthquake epicenters in the Atlantic lined up almost perfectly with Tharp's Rift Valley. The earthquakes weren't scattered randomly across the ocean floor. They were concentrated right along that central crack in the ridge. That was a powerful clue. Something active was happening there. Something dynamic. Around the same time, a geologist named Harry Hess at Princeton was thinking along similar lines. Hess had served in the Navy during World War II, commanding a transport ship in the Pacific, and he'd kept the ship's sonar running almost continuously during his voyages, quietly mapping the seafloor while he went about his military duties. After the war, he studied those readings and developed a radical hypothesis that he published in 1962 in a paper he half-jokingly called an essay in geopoetry, as if to soften the blow of how speculative it was. His idea was this: the ocean floor is not permanent. It's being continuously created at the mid-ocean ridges, where hot material from the Earth's interior rises up, cools, and forms new crust. That new crust then moves slowly away from the ridge on both sides, like a pair of enormous conveyor belts. And at the edges of the oceans, where the seafloor meets a continent, the old oceanic crust dives back down into the Earth's interior, recycling itself. Hess called this seafloor spreading. Think about what that means for a second. The ocean floor isn't ancient. It's not some primordial surface that's been sitting there since the Earth formed. It's young. It's constantly being renewed. The oldest oceanic crust on the planet is only about 200 million years old, which sounds like a lot until you realize the Earth itself is 4.5 billion years old. The continents have rocks that are billions of years old, but the ocean floor, it's practically brand new by geological standards. It's being made and destroyed all the time in a slow, continuous cycle. And here's the thing. This was the missing mechanism. This was what Wegener couldn't find. The continents aren't plowing through the ocean floor like ships through ice. They're riding on top of much larger plates that include both continental and oceanic crust, and those plates are being moved by the creation and destruction of oceanic crust at ridges and trenches. The continents are passengers, not drivers. They're carried along by the motion of the plates beneath them, the way a package on a conveyor belt doesn't push itself, it's carried by the belt. But Hess's idea, elegant as it was, still needed proof, and the proof came from an unexpected direction: magnetism. In the early 1960s, two British geologists, Fred Vine and Drummond Matthews, along with their supervisor at Cambridge, made a discovery that essentially clinched the case for seafloor spreading. They were studying the magnetic properties of the rocks on the ocean floor near the mid-ocean ridges, and they found something beautifully strange. Here's what you need to know about Earth's magnetic field to understand this. The Earth acts like a giant magnet, with a magnetic north pole and a magnetic south pole, and that's why compasses work. The needle aligns with the field. But here's what's wild. The Earth's magnetic field isn't constant. It flips. Every few 100,000 years on average, though the timing is irregular, the magnetic poles reverse. North becomes south, south becomes north. If you'd been holding a compass 780,000 years ago, the needle would have pointed south instead of north. We don't fully understand why this happens. It has to do with the churning of molten iron in the Earth's outer core. But we know it happens because the evidence is written in the rocks. When volcanic rock cools and solidifies, tiny magnetic minerals inside it, mostly a mineral called magnetite, align themselves with whatever the Earth's magnetic field is at that moment, like tiny compass needles freezing in place. Once the rock hardens, those minerals are locked in. They become a permanent record of what the magnetic field looked like when that rock formed. So if you can measure the magnetism of old rocks, you can figure out which direction the Earth's magnetic field was pointing when those rocks solidified. And what Vine and Matthews found when they surveyed the rocks on either side of the mid-Atlantic ridge was a pattern of magnetic stripes. Bands of rock with normal polarity, matching today's magnetic field, alternating with bands of reversed polarity, where the frozen magnetic minerals pointed the other way. And these stripes were symmetrical. They mirrored each other on either side of the ridge, like a barcode split down the middle. Think about why that would happen. If new rock is being created at the ridge as magma wells up and cools, it records the current magnetic field. Then it gets pushed aside as more new rock forms behind it. If the magnetic field flips, the next batch of rock records the reversed field. Flip again, and the next batch records normal polarity again. Over millions of years, you get this beautiful zebra stripe pattern spreading out from the ridge on both sides, a tape recording of the Earth's magnetic history, written in stone on the ocean floor. When Vine and Matthews published their findings in 1963, it was like the last tumbler clicking into place in a lock. Seafloor spreading was real. The ocean floor was moving. And if the ocean floor was moving, then the continents were moving with it. Wegener had been right all along, not about the mechanism, but about the fundamental observation. The continents drift. The Earth's surface is in motion, and now the pieces started falling together fast. Throughout the mid-1960s, a whole generation of geologists and geophysicists took these ideas: continental drift, seafloor spreading, the patterns of earthquakes and volcanoes, and assembled them into a unified theory. They called it plate tectonics, and it was published in a series of landmark papers between about 1965 and 1968. The core idea is deceptively simple. The Earth's outer shell, A layer called the lithosphere, which includes the crust and the uppermost part of the mantle, is broken into a number of rigid plates. These plates float on a hotter, softer layer beneath them, called the asthenosphere, which behaves almost like an extremely viscous fluid over long timescales. The plates move, they interact at their boundaries, and almost everything dramatic that happens on the Earth's surface, earthquakes, volcanoes, mountain building, happens at those boundaries. There are about 15 major plates and a bunch of smaller ones, and they fit together like a cracked eggshell wrapped around the planet. The Pacific Plate, the North American Plate, the Eurasian Plate, the African Plate, the Antarctic Plate, each one a vast slab of rock, some carrying continents, some entirely oceanic, some a mix of both, and they're all moving all the time at speeds of roughly 1 to 10 centimeters per year, about as fast as your fingernails grow. You'd never feel it, you'd never notice, but over millions of years, those centimeters add up to thousands of miles, rearranging the entire face of the planet. Now, what drives this motion? What actually pushes and pulls these enormous plates? That's a question that even today doesn't have a single clean answer. It's probably a combination of forces. There's the pull of gravity on the dense, cold edge of a plate as it sinks back into the mantle at a subduction zone. That's called slab pull, and many geophysicists think it's the dominant force. There's ridge push, where the elevated mid-ocean ridge essentially slides the plate downhill, away from the ridge under its own weight. And there's the drag of convection currents in the mantle. Hot material rising, spreading laterally, cooling, and sinking back down in enormous slow-motion loops that might help drag the plates along from below. The relative importance of each force is still debated, and it probably varies from plate to plate. But the motion itself is not debated. We can measure it now, directly, using GPS satellites down to fractions of a millimeter per year. The plates are moving. That's just a fact. And the boundaries where those plates meet, those edges where one plate grinds against another, or pulls away, or dives beneath, those are where the story of earthquakes really begins. Because an earthquake, at its most fundamental, is what happens when the slow, patient motion of the plates builds up stress in the rock until the rock can't take it anymore and it breaks. It snaps. And in that instant of breaking, all that stored energy that's been accumulating for years, decades, sometimes centuries, releases in a burst of seismic waves that radiate outward through the earth. That's an earthquake. That's all an earthquake is. Stored stress, sudden failure, released energy. But the way that plays out in practice, the sheer mechanics of how rock fails, and what happens at those plate boundaries, that's where things get really interesting. So let's think about what's actually happening down there, in the rock, at the boundary between two plates. Imagine you take a wooden stick, a pencil say, and you hold one end in each hand and you start bending it. Slowly. At first, the wood flexes. It absorbs the stress. It deforms a little, elastically, meaning if you let go, it'd spring right back to its original shape. But you keep bending, you keep applying force, and at some point, the wood can't flex any further. It snaps, and when it snaps, the two halves spring back past their original position, vibrating, and you hear that sharp crack. That crack is a tiny earthquake. The snap is the fault rupturing. The vibration is the seismic wave. And the springing back, that's what seismologists call elastic rebound. This idea, elastic rebound, is one of the most important concepts in earthquake science, and it was first clearly articulated by a man named Harry Fielding Reid after the Great San Francisco Earthquake of 1906. Now, that earthquake April 18, 1906, 5:12 in the morning, that one deserves some time. Because it wasn't just a disaster. It was a turning point in how we understand what earthquakes physically are. The earthquake struck along the San Andreas Fault, which runs roughly north-south through California for about 800 miles. The rupture that morning was enormous. The fault broke along a stretch of nearly 300 miles, from the town of San Juan Bautista in the south all the way up past Point Arena in the north. In San Francisco itself, the shaking lasted about 45 to 60 seconds. Buildings collapsed, chimneys fell, streets buckled. But the real catastrophe came after. Fires broke out across the city, fed by ruptured gas mains, and the water mains were broken too, so firefighters couldn't stop them. The fires burned for 3 days and destroyed about 80% of the city. Over 3,000 people died. More than half the city's population, over 200,000 people, were left homeless. But here's what matters for our story. After the earthquake, the state of California appointed a commission to study it, led by a geologist named Andrew Lawson, and one of the key investigators was Harry Fielding Reid, a professor of geophysics at Johns Hopkins University. Reid did something remarkably clever. He looked at survey data, measurements of the positions of roads, fences, and other landmarks that had been taken before the earthquake, some of it decades before. And he compared those positions to new surveys taken after the earthquake. What he found was striking. On either side of the San Andreas Fault, the ground had been slowly shifting for years before 1906. Points on the western side of the fault had been creeping northward relative to points on the eastern side. Slowly, steadily, year after year. But right at the fault itself, the two sides were locked together by friction. They weren't sliding past each other. They were stuck. So think about what that means. The rock far from the fault is moving, driven by the plate motion. But the rock right at the fault can't move because the two surfaces are locked together, gripping each other. So the rock near the fault is being bent, deformed, like that pencil in your hands. It's storing elastic energy, and it keeps storing it year after year until the stress exceeds the friction holding the fault together. And then, snap, the fault ruptures. The two sides lurch past each other. The rock springs back to its unstressed shape, and all that stored energy radiates outward as seismic waves. Reid called this the elastic rebound theory, and it was published in 1910, and it remains the foundation of how we understand earthquakes to this day. Now, the place where the fault actually breaks, where the rupture begins, that's called the focus, or the hypocenter. It's usually underground, sometimes quite deep, sometimes shallow. The point on the Earth's surface directly above the hypocenter, that's the epicenter. You hear that word on the news all the time, right? The epicenter was located 12 miles southeast of... Now, you know exactly what it means. It's just the spot on the surface above where the fault first gave way. And here's something that might surprise you. The rupture doesn't happen all at once along the entire fault. It starts at one point, the hypocenter, and then it propagates, it spreads, along the fault surface, kind of like a zipper unzipping, or like a crack spreading across a windshield. The speed of that rupture propagation is fast, typically about 2 to 3 kilometers per second, roughly 70 to 80% of the speed of the shear waves in the surrounding rock. For a big earthquake, where the fault might rupture along hundreds of kilometers, that means the rupture process itself can take 30 seconds, a minute, even longer. The earthquake you feel isn't one single jolt. It's the accumulated effect of the fault unzipping over a large area, with seismic waves arriving from different parts of the rupture at slightly different times. And the energy that gets released. Let's talk about that for a second, because the numbers are genuinely staggering. You've heard of the Richter scale, of course. Everyone has. Charles Richter and Benno Gutenberg developed it in 1935 at Caltech. The key thing to understand about it is that it's logarithmic. Each whole number step up represents roughly 32 times more energy released. So a magnitude 6 earthquake releases about 32 times more energy than a magnitude 5. A magnitude 7 releases about 32 times more than a 6, which means it releases about 1,000 times more energy than a 5. A magnitude 9 releases about 32,000 times more energy than a magnitude 7. The numbers get absurd very quickly. The 2011 Tohoku earthquake off the coast of Japan, magnitude 9.1, released energy equivalent to roughly 600 million times the energy of the Hiroshima atomic bomb. Just sit with that number for a moment. 600 million Hiroshimas. All from stress that had been quietly, invisibly accumulating in rock for centuries. Now, the original Richter scale had some limitations. It worked best for local earthquakes in Southern California using a specific type of seismograph. So today, seismologists mostly use what's called the moment magnitude scale, which is based on a quantity called the seismic moment. The seismic moment takes into account three things: how stiff the rock is, how large the area of the fault that ruptured, and how far the two sides of the fault actually slipped past each other. It's a more physically meaningful measure, and it works for earthquakes of all sizes and at all distances. But the numerical values are designed to be roughly consistent with the old Richter scale. So for most practical purposes, when you hear someone say magnitude 6.2, you don't really need to worry about which scale they're using. The number means roughly the same thing. So we've got plates moving, stress building at their boundaries, faults locking and then rupturing, energy radiating outward. But not all plate boundaries are the same, and the type of boundary determines the character of the earthquakes you get. Let's walk through them, because this is where the geology really starts to shape the hazard. At divergent boundaries, places where plates are pulling apart, like the Mid-Atlantic Ridge that Marie Tharp mapped, the earthquakes tend to be relatively small and shallow. The crust is being stretched and thinned, it's hot, and the faults don't build up enormous amounts of stress before they slip. You get lots of little earthquakes, magnitude 5 and below mostly. Iceland sits right on the Mid-Atlantic Ridge, and Icelanders feel small earthquakes regularly. They're a fact of life there, but they rarely cause serious damage. Transform boundaries, where plates slide horizontally past each other, those produce bigger earthquakes. The San Andreas Fault is the classic example. It's a transform boundary where the Pacific Plate is sliding northwest relative to the North American Plate at about 46 millimeters per year. These faults can lock for long periods and then release in major events. The 1906 San Francisco earthquake was one. The 1857 Fort Tejon earthquake in Southern California was another, estimated at about magnitude 7.9. The thing about transform faults is that the earthquakes can be very large, up to about magnitude 8 or so, but they're generally not the absolute largest earthquakes on Earth. That distinction belongs to a different type of boundary entirely: convergent boundaries, places where plates collide, and specifically subduction zones, where one plate dives beneath another into the mantle. These are the monsters. These are where you get the biggest earthquakes our planet is capable of producing, and the reason is almost intuitive once you think about it. At a subduction zone, the contact area between the two plates The fault surface is enormous. It's not a vertical crack like the San Andreas. It's a gently dipping plane, angled maybe 10 to 30 degrees, and it extends for hundreds of kilometers along the coast and hundreds of kilometers down into the earth. That means the locked area, the area where stress can accumulate, is vast. And when it finally lets go, the rupture can be immense. Every single earthquake above magnitude 9 that we've ever recorded has occurred at a subduction zone. The 1960 Chilean earthquake, magnitude 9.5, the largest ever recorded, subduction zone. The 1964 Alaska earthquake, magnitude 9.2, subduction zone. The 2004 Indian Ocean earthquake, magnitude 9.1, subduction zone. The 2011 Tohoku earthquake, subduction zone. There's a pattern here, and it's not a coincidence. It's physics. It's geometry. The bigger the fault area that can lock and then rupture, the bigger the earthquake you can get. And at subduction zones, there's another factor that makes things especially dangerous. Something that connects the earthquake to the ocean in a way that can turn a disaster into a catastrophe. Because when a subduction zone ruptures, it doesn't just shake the ground. It moves the ocean floor. Think about what's happening down there. You've got this enormous slab of oceanic crust diving beneath a continental plate. And for decades, maybe centuries, the two plates are locked together by friction. The overriding plate, the one on top, is being slowly dragged downward and compressed by the motion of the subducting slab beneath it. It's like someone is pulling the edge of a diving board down, bending it, loading it with elastic energy. And then the fault ruptures, and that overriding plate snaps back upward. In the 2011 Tohoku earthquake, parts of the seafloor were thrust upward by as much as 5 meters in an instant. 5 meters. That's a 2-story wall of rock, suddenly displacing the entire water column above it. And the ocean doesn't compress. Water is essentially incompressible. So when you shove the seafloor up by 5 meters across an area hundreds of kilometers long, you are lifting a volume of water that is almost beyond comprehension. And that displaced water has to go somewhere. That's a tsunami. And here's the thing that makes tsunamis so different from ordinary ocean waves. A normal wave, the kind you see at the beach, is generated by wind. It affects only the surface layer of water. Even a big storm wave might only involve the top 10 or 20 meters of ocean. But a tsunami involves the entire water column, from the surface all the way down to the seafloor. In the deep ocean, that might be 4 kilometers of water, all moving together. And in deep water, a tsunami doesn't look like much. It might only be half a meter high at the surface. You could be on a ship in the open Pacific, and a tsunami could pass right under you and you'd barely notice. Just a gentle rise and fall over a period of maybe 15 or 20 minutes. But it's moving fast. Incredibly fast. In deep water, the speed of a tsunami is roughly equal to the square root of the gravitational acceleration times the water depth. In 4,000 meters of water, that works out to about 700 kilometers per hour. That's roughly the cruising speed of a commercial jet. So this wave, this barely perceptible rise in the open ocean, is crossing the Pacific at the speed of a Boeing 747. And then it reaches shallow water, and everything changes. As the water gets shallower near the coast, the wave slows down. The front of the wave is in shallower water, moving slower, while the back of the wave is still in deeper water, still moving fast, so the wave compresses. All that energy, spread across 4 kilometers of water depth in the open ocean, is now being squeezed into a water column that might be only 50 meters deep, then 20, then 10. The wave height grows. What was half a meter in the deep ocean becomes 1 meter, then 3, then 10, then in extreme cases 30 meters or more. And it's not a breaking wave like a surfer rides. It's more like the entire ocean rising, relentlessly, pushing inland with a force that is almost impossible to resist. It's a wall of water that just keeps coming, carrying cars and boats and buildings and trees, and it doesn't stop for minutes. The 2004 Indian Ocean tsunami is probably the most devastating example in living memory. On December 26, 2004, a magnitude 9.1 earthquake ruptured along roughly 1,300 kilometers of the Sunda megathrust, the subduction zone where the Indo-Australian plate dives beneath the Burma microplate just off the west coast of Sumatra. The rupture lasted about 10 minutes of continuous fault slip, propagating northward from the initial breakpoint. The seafloor was displaced by up to 15 meters in some areas, and because this subduction zone runs roughly north-south, the tsunami radiated outward mainly to the east and west. It struck the coast of Sumatra within about 20 minutes. It crossed the Bay of Bengal and hit Sri Lanka and the east coast of India about 2 hours later. It reached the coast of East Africa, more than 5,000 kilometers away, about 7 hours after the earthquake. By the time it was over, approximately 230,000 people had died across 14 countries. It remains one of the deadliest natural disasters in recorded history. And here's what made it so much worse than it needed to be. There was no tsunami warning system in the Indian Ocean in 2004. The Pacific Ocean had one. It had been operating since 1949, established after a tsunami generated by a 1946 earthquake in the Aleutian Islands struck Hilo, Hawaii, killing 159 people. That system used seismographs to detect large earthquakes and tide gauges to confirm tsunami waves, and it could issue warnings to Pacific Rim countries within minutes. But no equivalent system existed for the Indian Ocean. There had been discussions about building one. Scientists had pointed out that the Sunda megathrust was perfectly capable of generating a massive tsunami. But the infrastructure wasn't there. The warnings weren't there. In many of the affected areas, people had no idea what was happening. Some people actually walked out onto the exposed seafloor when the water receded before the main wave arrived, not understanding that the withdrawal of the ocean is one of the most dangerous warning signs of an incoming tsunami. They were curious. They went to look at the fish flopping on the suddenly dry seabed, and then the wave came. After 2004, everything changed. The Indian Ocean Tsunami Warning System was established and became operational by 2006. Deep ocean pressure sensors, called DART buoys for deep ocean assessment and reporting of tsunamis, were deployed across the Indian Ocean. These sight on the seafloor and can detect the passage of a tsunami wave in the open ocean by measuring tiny changes in water pressure. Changes as small as a fraction of a centimeter in water depth, even under 4,000 meters of ocean. When they detect a wave consistent with a tsunami, they transmit data via satellite to warning centers, which can then issue alerts to coastal communities. It's a system born directly from tragedy, from the recognition that the science existed, the understanding existed, but the infrastructure to save lives did not. Now, the 2011 Tohoku earthquake and tsunami is a different kind of story, because Japan did have a warning system. Japan probably had the most sophisticated earthquake and tsunami preparedness infrastructure on Earth. They had seawalls, they had evacuation routes, they had education programs, they had the most advanced seismic monitoring network anywhere, and the earthquake still overwhelmed their preparations. The magnitude 9.0 rupture generated tsunami waves that reached heights of up to 40 meters in some locations along the coast. 40 meters. That's roughly the height of a 13-story building. Seawalls that had been designed for waves of 5 or 6 meters were simply overtopped. Entire towns were swept away. Nearly 20,000 people died. And here's where the engineering story gets really interesting and really sobering. The seawalls had been designed based on historical records. Engineers and planners had looked at the historical record of tsunamis along the Sanriku coast and designed their defenses to withstand the largest events they could find evidence for. But the 2011 event was larger than anything in the historical record for that particular section of the fault. There were geological clues, sediment deposits from ancient tsunamis that suggested events of similar magnitude had occurred roughly every 1,000 years. But those clues hadn't been fully incorporated into the engineering design standards. The assumption had been that the northern Japan subduction zone couldn't produce a magnitude 9 earthquake. The fault segments were thought to be too segmented, too broken up, to rupture all at once. That assumption was wrong. Multiple segments ruptured together in a cascading failure, producing a single enormous earthquake that nobody's models had predicted. This gets at something really fundamental about earthquake engineering and hazard assessment. We're always working with incomplete information. The historical record of earthquakes is, geologically speaking, incredibly short. Written records go back maybe a few thousand years, in the best cases, in China, in the Mediterranean. In many parts of the world, reliable records only go back a few hundred years or less. And the biggest earthquakes on the biggest faults might have recurrence intervals of 500, 1,000, even several thousand years. So we might be looking at a fault that hasn't produced a major earthquake in recorded history and conclude that it's safe, when really we're just looking at a snapshot that's too short to capture the full range of what that fault can do. This is exactly what happened with the Cascadia subduction zone, which runs along the Pacific Northwest coast of North America, from Northern California up through Oregon and Washington and into British Columbia. For most of the 20th century, this subduction zone was considered relatively benign. There were no large earthquakes in the historical record. The indigenous oral histories of the region contained stories of great shaking and flooding, but those weren't taken seriously by the scientific establishment for a long time, and the assumption was that the Cascadia subduction zone was somehow different, that it was slipping smoothly, aseismically, rather than locking up and building toward a large earthquake. And then, in the late 1980s, a geologist named Brian Atwater started digging into the coastal marshes of Washington state, literally digging. He found layers of buried marsh soil, dark, organic, root-filled soil that had suddenly dropped below sea level and been covered by sand. The interpretation was startling. The marsh soil represented stable land that had been slowly deformed upward by the locked subduction zone, just like that diving board being pulled down. And then, suddenly, the fault had ruptured, the land had dropped, and a tsunami had washed sand over the drowned marsh. And it hadn't happened just once. Atwater found evidence of multiple such events, spaced roughly 300 to 500 years apart, going back several thousand years. The most recent one appeared to have happened about 300 years ago. And here's where the detective work gets really beautiful. Japanese historical records, meticulous records kept by coastal communities for centuries, documented what they called an orphan tsunami that struck the coast of Japan on January 27, 1700. An orphan tsunami is one that arrives without any preceding earthquake being felt locally. The Japanese felt no earthquake, but the tsunami came anyway, damaging homes and flooding rice paddies. Working backward from the arrival time of that tsunami, accounting for the travel time across the Pacific, Scientists calculated that it must have been generated by an earthquake on the evening of January 26, 1700, local time, along the Cascadia subduction zone. The estimated magnitude was about 9.0. So here was a subduction zone, right along the coast of the Pacific Northwest, capable of producing a magnitude 9 earthquake and a massive tsunami, and it had done exactly that just 300 years ago. And it will do it again. The question isn't whether, it's when. And this realization, which really crystallized in the 1990s and 2000s, has fundamentally changed how engineers and planners in the Pacific Northwest think about everything. Buildings, bridges, emergency plans, school construction codes, hospital retrofits, all of it has had to be reconsidered in light of the fact that the ground beneath Seattle, Portland, Vancouver, and dozens of smaller communities is sitting on a ticking geological clock. And that word, ticking, is worth pausing on for a moment, because it captures something important about how earthquake hazard actually works in subduction zones. Remember, the Juan de Fuca plate is still diving beneath North America right now, tonight, as you're lying there. It hasn't stopped. The plates are converging at roughly 40 millimeters per year, a little over 1.5 inches. And because the fault is locked, all of that motion is being stored as elastic strain in the rocks on both sides of the boundary. Every year that passes without a rupture, the system accumulates more energy. It's been over 320 years since the last great Cascadia earthquake. At 40 millimeters per year, that's something like 13 meters of accumulated slip, over 40 feet of motion that the fault owes the earth, so to speak. When it finally lets go, all of that stored displacement will be released in a matter of minutes. The seafloor will lurch, the coastline will drop, and a tsunami will cross the Pacific. So, how do you prepare for something like that? How do you engineer a city for an earthquake that hasn't happened in living memory, that no one alive has ever experienced, but that geology tells you is inevitable? This is one of the deepest challenges in earthquake engineering, and it forces us to talk about something that might sound dry at first, but is actually fascinating once you dig into it: building codes. I know. Building codes don't sound like the stuff of drama. But here's the thing. Building codes are where the rubber meets the road. They're where scientific understanding of earthquakes gets translated into actual decisions about how thick a column should be, how much steel goes into a foundation, how a hospital is anchored to the ground. And the history of how those codes have evolved is really a story about how societies learn from disasters, often too slowly, and almost always at a terrible cost. Let's go back a bit. For most of human history, buildings were designed based on tradition and experience. You built things the way your father built them, the way his father built them. In earthquake-prone regions, local building traditions sometimes evolved clever solutions. Traditional Japanese wooden architecture, for instance, with its flexible joints and lightweight materials, was remarkably earthquake-resistant, even though the builders couldn't have explained the physics of why. They just knew, from generations of experience, that rigid masonry crumbled and flexible wood survived. But as cities modernized in the 19th and 20th centuries, those traditional building methods were often abandoned in favor of unreinforced masonry, concrete, and steel frame construction, materials and methods imported from regions where earthquakes weren't a concern. And when earthquakes struck these modernized cities, the results were catastrophic. The 1906 San Francisco earthquake, which we talked about earlier in the context of Harry Fielding Reid and elastic rebound theory, was also a watershed moment for building codes. The earthquake itself was devastating, but what made it truly catastrophic was the fire that followed. Broken gas mains, ruptured water lines, collapsed buildings trapping people. The fire burned for 3 days and destroyed about 80% of the city. Over 3,000 people died, and more than half the city's population of 400,000 was left homeless. And here's what's important from an engineering perspective. When they rebuilt San Francisco, they didn't fundamentally change how they built. There was enormous political and economic pressure to rebuild quickly, to project an image of resilience, and to avoid anything that might discourage investment. The lessons of 1906 were, in many ways, deliberately suppressed. It took another disaster to really get the conversation moving. The 1933 Long Beach earthquake in Southern California was only a magnitude 6.4, not even close to the scale of 1906, but it caused tremendous damage, particularly to schools. Unreinforced masonry school buildings collapsed or were severely damaged across the region. By sheer luck, the earthquake struck at 5:54 in the evening, after school hours. If it had hit during the school day, hundreds or possibly thousands of children would have been killed. The near miss was so horrifying that the California State Legislature passed the Field Act just 1 month later, in April 1933, mandating earthquake-resistant design standards for all new public school buildings in California. It was one of the first seismic building codes in the United States, and it happened because people could imagine their children crushed under rubble. That's a pattern you see again and again in earthquake engineering history. The codes don't get written because scientists publish papers. They get written because something terrible happens, or nearly happens, and the public demands action. It's reactive, not proactive. And that's a problem when you're dealing with hazards that recur on timescales of centuries. Now, the basic idea behind earthquake-resistant design is actually pretty intuitive once you think about it. An earthquake shakes the ground. The ground moves sideways, back and forth, sometimes violently. A building sitting on that ground wants to stay still. Newton's first law, inertia. So the ground moves one way, and the building's base moves with it. But the upper floors lag behind. This creates lateral forces, sideways forces, throughout the structure. And most buildings, historically, were designed to handle vertical loads just fine. Gravity pulls down, the walls and columns push up, everything's in equilibrium. But sideways forces? That's a completely different problem. Think about it like this. Take a tall stack of books and set it on a table. Push down on the top of the stack. It's perfectly stable. The books can handle that compressive load all day. But now, give the table a sharp sideways shove. The whole stack topples. It had no lateral resistance. That's essentially what happens to unreinforced masonry buildings in an earthquake. They're great at handling the weight of their own floors and roof, but the moment the ground moves sideways, the walls crack, the floors lose their support, and the whole thing pancakes. So earthquake-resistant design is fundamentally about giving buildings the ability to handle lateral forces, and there are several strategies for doing this, each with its own engineering logic. The simplest approach is just to make the building stronger. Add more walls, thicker columns, cross-bracing, shear walls. A shear wall is basically a stiff, strong wall that resists sideways deformation. If you've ever seen the big concrete walls in a parking garage or a stairwell core, those are often functioning as shear walls. They're the building's defense against lateral forces. You can also use diagonal bracing in steel frames, those X-shaped or V-shaped steel members you sometimes see on the outside of buildings. They triangulate the frame, and triangles, as any engineer will tell you, are inherently rigid shapes. You can deform a rectangle by pushing on one corner, turning it into a parallelogram. But you can't deform a triangle without changing the length of one of its sides. So bracing a rectangular frame with diagonal members makes it much stiffer and stronger against sideways forces. But here's where it gets interesting. Stiffness isn't always your friend in an earthquake. A very stiff building will resist the ground motion up to a point, but if the earthquake is strong enough, the forces can exceed what the structure can handle, and it fails suddenly and catastrophically. A brittle failure. Think of a dry twig. It's stiff, it resists bending, and then it snaps. What you actually want, in many cases, is ductility, the ability to deform without breaking. A green twig. You can bend it way past where a dry twig would snap, and it just keeps bending. It absorbs the energy of the deformation without fracturing. This insight, that ductility is often more important than raw strength, was one of the most important conceptual shifts in earthquake engineering, and it really took hold in the latter half of the 20th century. Modern seismic design codes don't just require buildings to be strong enough to resist earthquake forces. They require buildings to be detailed, and that's the actual engineering term, detailed, in ways that ensure ductile behavior, the connections between beams and columns, the way reinforcing steel is arranged inside concrete, the specific geometry of joints. All of these details determine whether a structure will bend gracefully or shatter suddenly when pushed beyond its elastic limit. And this brings us to one of the most tragic lessons in earthquake engineering history. The 1988 Spitak earthquake in Armenia, then part of the Soviet Union. It was a magnitude 6.8, which is significant but not enormous. But it killed roughly 25,000 people, injured tens of thousands more, and left 500,000 homeless. The devastation was concentrated in cities like Spitak, Leninakan, and Kirovakan, where Soviet-era precast concrete apartment buildings collapsed en masse. These buildings were constructed from large prefabricated concrete panels, bolted and welded together. They were efficient to build. You could assemble an entire apartment block in weeks, but the connections between the panels were brittle. When the earthquake hit, the connections failed, the panels separated, and the floors fell straight down, one on top of another, crushing everyone inside. The term for this is pancake collapse, and it's exactly as horrifying as it sounds. The Spitak earthquake exposed a fundamental flaw in how those buildings were designed. They had been engineered primarily for gravity loads and for the harsh Armenian winters. Thick concrete panels provided good insulation. But the seismic detailing was inadequate. The connections weren't designed to be ductile. They couldn't absorb and redistribute the energy of the earthquake. And so, a moderate earthquake, one that well-designed buildings could have survived with repairable damage, instead became a mass casualty event. You see this same lesson repeated in earthquake after earthquake around the world. The 1999 Izmit earthquake in Turkey, magnitude 7.6, killed over 17,000 people, many of them in mid-rise concrete apartment buildings that collapsed due to poor construction practices and inadequate seismic detailing. Investigations afterward revealed that many buildings had been constructed with substandard concrete, insufficient reinforcing steel, and columns that were too weak relative to the beams they supported. There was a term that emerged from the Turkish engineering investigations: soft story collapse. A soft story is a floor that's significantly weaker or more flexible than the floors above it. Often it's the ground floor, where you might have large open spaces for shops or parking, with fewer walls to provide lateral resistance. The upper floors are stiffer because they have more partition walls, so when the earthquake hits, all the deformation concentrates in that weak ground floor, and it collapses while the upper floors remain relatively intact. They just drop straight down as a unit. You end up with a building that looks like someone kicked out its legs. And this isn't just a problem in developing countries with lax enforcement. San Francisco's Marina District, built on landfill from the 1906 earthquake rubble, suffered extensive soft-story collapses during the 1989 Loma Prieta earthquake, a magnitude 6.9 event whose epicenter was actually 60 miles away. Beautiful 3- and 4-story apartment buildings with garages on the ground floor simply folded at the base. The ground floor vanished, and the upper floors settled down to street level. Some of those buildings are still being retrofitted today. So here's the picture that emerges. We understand pretty well what earthquakes do to buildings. We understand the physics of lateral forces, the importance of ductility, the danger of soft stories and brittle connections. We have sophisticated computer models that can simulate how a building will respond to a specific ground motion record. We can design buildings that will survive even very large earthquakes with minimal structural damage, and we do in places like Japan, where seismic engineering is extraordinarily advanced. The technology exists. The problem is implementation. The problem is that most of the buildings in the world that are vulnerable to earthquakes were built before modern seismic codes existed, or were built in places where codes exist on paper but aren't enforced, or were built cheaply with inadequate materials and workmanship. The problem is economic. Retrofitting an existing building to meet modern seismic standards is expensive, sometimes so expensive that it's cheaper to tear it down and start over. And in cities like Portland or Seattle, where the Cascadia threat has only been fully appreciated for a few decades, there are thousands of unreinforced masonry buildings, old concrete structures, and soft-story apartment buildings that were built long before anyone knew a magnitude 9 earthquake was possible there. This is the challenge that keeps earthquake engineers up at night. Not the physics. The physics are well understood. It's the gap between what we know and what we've actually done about it. It's the fact that right now, tonight, there are schools and hospitals and apartment buildings in earthquake-prone cities around the world that will collapse in the next major earthquake. And everyone in the engineering community knows it. And the retrofitting is happening too slowly because it costs too much, and the political will isn't there until after the disaster. That's the pattern. That's always been the pattern. The codes get written in blood, as engineers sometimes say, and the retrofitting only gets funded after the funerals. But let's talk about what happens when a society actually commits to doing something about it, because there is a place that has gone further than anywhere else on Earth in preparing for earthquakes, and that place is Japan. And the story of how Japan got there is worth spending some time on, because it shows both what's possible and what the limits of preparation really are. Japan sits at one of the most seismically violent intersections on the planet. You've got the Pacific Plate diving under the North American Plate, and yes, the northern part of Japan actually sits on the North American Plate, which surprises a lot of people. You've got the Philippine Sea Plate pushing in from the south. You've got the Eurasian Plate involved too. It's a tectonic pileup, basically. Japan experiences roughly 1,500 earthquakes a year that are strong enough to be felt by people, and a significant destructive earthquake every decade or so on average. So the Japanese relationship with earthquakes is ancient and deeply embedded in the culture, in the architecture, in the language itself. The word for earthquake in Japanese, jishin, has been part of the vocabulary for centuries. Early Japanese buildings, those beautiful wooden temples and pagodas, were actually remarkably earthquake resistant, almost by accident. The flexible wooden joinery, the heavy tile roofs that pressed the structure together, the way the interlocking brackets could absorb lateral movement. The 5-story pagoda at Horyuji Temple near Nara has been standing since the 7th century, 1,300 years, through countless earthquakes. And there's an engineering reason for that. The central pillar, the Shinbashira, acts almost like a tuned mass damper, swinging independently of the floors and counteracting the building's sway. Engineers didn't fully understand why pagodas survived so well until the 20th century, but the builders knew, intuitively, through generations of trial and error, that this design worked. The modern chapter of Japanese earthquake engineering really begins with the Great Kanto earthquake of September 1st, 1923. This was a magnitude 7.9 event that struck the Tokyo-Yokohama metropolitan area at about 2 minutes before noon, when millions of charcoal cooking fires were lit for the midday meal. The shaking was devastating on its own. It lasted between 4 and 10 minutes in various locations, which is an extraordinarily long duration. But the fires were what turned it into one of the deadliest natural disasters in recorded history. Firestorms swept through the densely packed wooden neighborhoods of Tokyo and Yokohama, creating their own weather, generating tornado-like fire whirls. In one incident that still haunts Japanese collective memory, about 38,000 people who had gathered in an open space called the Rikugun Honjo Hifukusho, a former military clothing depot, were killed in minutes when a massive fire whirl engulfed the area. The total death toll was around 105,000 people, with some estimates running higher. Entire cities were leveled. It was, at the time, the worst natural disaster in Japanese history. And here's what happened next, and this is where Japan's story diverges from so many others. Instead of just rebuilding and moving on, Japan institutionalized earthquake research and earthquake-resistant construction in a way that no country had done before. The Earthquake Research Institute was established at the University of Tokyo in 1925. Building codes were strengthened, and crucially, the culture shifted. Earthquakes weren't treated as acts of divine punishment or random misfortune. They were treated as an engineering problem that demanded an engineering solution. September 1st became Disaster Prevention Day, a national observance that continues to this day, with annual drills involving millions of people. But the codes kept evolving, and they evolved the same way codes evolve everywhere, through failure. The 1948 Fukui earthquake killed nearly 4,000 people and exposed weaknesses in the post-war building standards. The code was revised. The 1964 Niigata earthquake revealed the terrifying phenomenon of soil liquefaction on a massive scale. Buildings that were structurally sound simply toppled over sideways because the ground beneath them turned to liquid. And this is worth understanding for a moment, because liquefaction is one of those things that seems almost impossible until you see it happen. Think about wet sand at the beach. When you're standing still on it, it feels solid. But if you start wiggling your feet back and forth, the sand loosens up, water fills the gaps between the grains, and suddenly your feet are sinking. That's essentially what happens during liquefaction, but on a massive scale. When seismic waves pass through loose, water-saturated sandy soil, the shaking causes the soil grains to lose contact with each other. The water pressure between the grains increases until the soil essentially behaves like a liquid rather than a solid. Buildings can sink, tilt, or topple. Underground structures like sewer pipes and storage tanks can actually float to the surface because they're less dense than the liquefied soil around them. In Niigata in 1964, entire apartment buildings tilted over at crazy angles. There are famous photographs of 4-story reinforced concrete buildings lying on their sides, structurally intact, but completely unusable because the ground just gave way beneath them. The buildings didn't fail. The ground failed. And that distinction matters enormously in earthquake engineering, because it means you can design the most brilliant structure in the world, but if you build it on the wrong soil without proper foundation engineering, none of that matters. After Niigata, Japanese codes began incorporating soil analysis requirements much more rigorously. And then came 1995, and the earthquake that changed everything again. The Great Hanshin earthquake, also known as the Kobe earthquake. January 17th, 1995, magnitude 6.9, directly beneath the city of Kobe, a modern, prosperous city of 1.5 million people. The death toll was around 6,400, with over 40,000 injured and roughly 300,000 left homeless. And this one shocked Japan to its core, because Kobe was supposed to be prepared. This was Japan, the country that took earthquakes more seriously than anywhere else. The buildings were engineered, the infrastructure was modern, and yet the Hanshin Expressway, an elevated highway, collapsed along a 600-meter stretch, lying on its side in a scene that looked disturbingly similar to what had happened to the Cypress Street Viaduct in Oakland during Loma Prieta 6 years earlier. Older buildings, particularly those built before the 1981 code revision, collapsed in huge numbers. The 1981 code had been a major upgrade. It introduced the concept of two-level design, where buildings had to resist moderate earthquakes without damage and resist severe earthquakes without collapse. But everything built before 1981 was grandfathered in. And those pre-1981 buildings were the ones that killed people in Kobe. The response, again, was to learn and adapt. Japan poured enormous resources into retrofitting infrastructure, especially elevated highways and bridges. They developed and deployed base isolation systems on a massive scale. And this is one of the most elegant ideas in earthquake engineering, so let's talk about it for a moment. The concept is beautifully simple. Instead of making a building strong enough to resist earthquake forces, you disconnect it from the ground. You put it on bearings, usually rubber and steel laminated pads, or sometimes friction pendulum bearings, that allow the ground to move underneath the building while the building itself stays relatively still. Imagine setting a book on a table and then sliding the table back and forth. The book slides with the table because of friction. Now imagine putting marbles under the book. The table slides, but the book barely moves. That's the basic idea of base isolation. The bearings absorb and deflect the seismic energy before it can enter the structure. Japan embraced this technology with characteristic thoroughness. Thousands of buildings in Japan now sit on base isolation systems, including hospitals, government buildings, data centers, even some residential apartment complexes. And the results have been remarkable. During the 2011 Tohoku earthquake, that magnitude 9 event we talked about earlier, base-isolated buildings in Tokyo, which is about 370 kilometers from the epicenter, experienced dramatically less shaking than conventionally founded buildings right next door. The technology works. It's proven. And yet, outside of Japan and a few other wealthy, seismically aware countries, it's barely used because it's expensive, because it requires sophisticated engineering, because it's hard to retrofit onto existing buildings, because, once again, the gap between what we know how to do and what we actually do is enormous. Japan also pioneered another approach: active and semi-active damping systems. These are devices installed in buildings that actively counteract seismic forces in real time. The most common type is the tuned mass damper, which is essentially a large mass, sometimes hundreds of tons, mounted near the top of a building on bearings or pendulums, designed to swing in the opposite direction of the building's motion and cancel out the sway. You might have heard of the famous one in Taipei 101, the skyscraper in Taiwan. A 730-ton steel sphere suspended between the 87th and 92nd floors, visible to visitors, swinging gently during typhoons and earthquakes to keep the building stable. It's become a tourist attraction in its own right. But Japan has hundreds of buildings with similar systems, many of them far less visible, but equally effective. And then there's the early warning system, which is something Japan has developed into an art form. Remember, seismic waves travel at different speeds. The P waves, those compressional waves, travel fastest, roughly 6 to 8 kilometers per second through the crust. The S waves, the shear waves that do most of the damage, travel slower, maybe 3.5 to 5 kilometers per second, and the surface waves are slower still. So if you have a dense network of seismometers near the earthquake source, you can detect the P waves within seconds of the rupture beginning, estimate the earthquake's location and magnitude almost instantly, and broadcast a warning to areas farther away before the destructive S waves and surface waves arrive. It's not a prediction. The earthquake has already started, but it's a head start. Maybe 5 seconds, maybe 30 seconds, if you're far enough from the epicenter. Japan's system, called J-Alert, integrated with the earthquake early warning system operated by the Japan Meteorological Agency, can push alerts to every cell phone in the country within seconds. Bullet trains automatically brake. Factory assembly lines shut down. Elevators stop at the nearest floor and open their doors. Gas valves close. And people drop, cover, and hold on. 5 seconds doesn't sound like much. But think about what you can do in 5 seconds. You can get under a desk. You can move away from a window. You can step back from a surgical table. A surgeon in an operating room, getting a 5-second warning, can withdraw a scalpel from a patient's body. 5 seconds can be the difference between life and death. And the system proved its value spectacularly during the 2011 Tohoku earthquake, when millions of people in Tokyo received warnings a full minute or more before the strongest shaking arrived because the epicenter was so far offshore. Other countries have been developing similar systems. Mexico has had one since 1991, called seismic, initially using sensors along the Guerrero coast to warn Mexico City, which sits about 300 kilometers inland. The United States has been building out Shake Alert along the West Coast, California, Oregon, Washington, and it's been operational in various stages since around 2019. It's not as mature as Japan's system yet, but it's getting there. And for a place like the Pacific Northwest, where a Cascadia megathrust event would generate shaking that takes minutes to propagate across the region, the potential warning time could be genuinely life-saving. But here's the thing that keeps nagging at the back of all this progress, all this technology, all this engineering brilliance. The 2011 Tohoku earthquake and tsunami killed nearly 20,000 people in the most seismically prepared country on Earth. The buildings mostly performed well, remarkably well actually, for a magnitude 9 event. The early warning system worked. The bullet train stopped safely. And yet 20,000 people died, almost all of them from the tsunami. The seawalls weren't high enough. The evacuation plans in some communities weren't adequate. Some people didn't evacuate because they trusted the walls. The nuclear power plant at Fukushima Daiichi had backup generators in the basement, where the tsunami flooded them, causing the meltdowns that forced the evacuation of 150,000 people and contaminated a wide area that remains partly uninhabitable today. And that failure at Fukushima, that was an engineering failure. but it was also a failure of imagination. The plant was designed to withstand a certain size tsunami based on historical records that didn't go back far enough. The engineers used the data they had, and the data wasn't sufficient. The same kind of problem Brian Atwater had uncovered with the Cascadia subduction zone. When your historical record is too short, you underestimate the hazard. So where does that leave us? It leaves us in a world where earthquake science and earthquake engineering have made extraordinary progress over the past century, where we understand the mechanics of plate tectonics and fault rupture and wave propagation and structural response with remarkable sophistication, and where the gap between that understanding and the actual safety of the built environment varies enormously from place to place, from building to building, from one side of a street to the other. And it leaves us with a question that isn't really an engineering question at all, but a human one. A question about risk and how we think about events that are almost certain to happen, but haven't happened yet. Because that's the strange psychological territory earthquakes occupy. They're not like hurricanes, where you can watch the storm forming on a satellite image days in advance, track its path, prepare in real time. They're not like floods, where you can see the river rising. Earthquakes give you no warning at all, or at best, a few seconds from an early warning system. And the big ones, the truly catastrophic ones, might come once every few hundred years on a given fault, which means most people living near that fault will go their entire lives without experiencing one. And that creates this bizarre relationship with risk, where intellectually, you know the danger is real, the scientists have told you, the evidence is overwhelming. But emotionally, experientially, it doesn't feel real. It feels abstract. It feels like something that happens to other people in other places at other times. There's actually a name for this. Psychologists call it normalcy bias, the tendency to assume that because something hasn't happened before in your experience, it won't happen. And it's incredibly powerful. You see it in every disaster. People who don't evacuate when they're told to. People who stand on the beach watching the ocean recede before a tsunami, curious rather than terrified, not recognizing the most obvious warning sign in nature. People who buy a house on a floodplain because it hasn't flooded in 20 years, as if 20 years of quiet means the river has forgotten how to rise. And with earthquakes, normalcy bias is especially potent because the return periods can be so long. The Cascadia subduction zone ruptures roughly every 200 to 500 years. The last one was in 1700. So nobody alive today has any memory of it. Nobody's grandparents had any memory of it. It exists only in the geological record and in the oral traditions of indigenous peoples who were there, and for a long time, mainstream science didn't listen to those traditions either. Here's what's really fascinating, though. The way different societies respond to this kind of risk tells you a lot about human nature, about politics, about economics, about culture, because the science is essentially the same everywhere. Seismologists in Japan, and seismologists in California, and seismologists in Turkey, and seismologists in Nepal are all working from the same physics, the same understanding of plate tectonics and fault mechanics. They share data, they publish in the same journals, they attend the same conferences. The knowledge is global, but the response to that knowledge, the translation of scientific understanding into actual preparedness, varies wildly. And the reasons are almost never scientific. They're economic, they're political, they're cultural, they're deeply, frustratingly human. Think about it this way. We know exactly what kind of building performs well in an earthquake. We've known for decades. You want a structure that's well connected. foundations tied to walls, walls tied to floors, floors tied to the roof, so the whole thing moves as a unit rather than coming apart. You want ductile materials that can flex and absorb energy rather than brittle ones that snap. You want a regular shape, because L-shaped or U-shaped buildings tend to tear themselves apart at the corners where the wings meet. You want the building anchored to its foundation, not just sitting on top of it. You want soft story problems addressed, those ground floor parking garages and storefronts with big open spans that collapse because they're so much weaker than the floors above. We know all of this. The engineering is mature. The building codes exist. And yet, right now, tonight, there are tens of millions of people around the world sleeping in buildings that would kill them in a moderate earthquake. Not because we don't know how to build safely, but because safe construction costs more money, and enforcing codes requires functioning institutions, and retrofitting old buildings is expensive and disruptive, and politicians don't get reelected by spending billions to prevent a disaster that might not happen during their term. That tension between what we know and what we do about it is maybe the central story of earthquake preparedness in the 21st century, and it plays out differently everywhere. Take the city of Istanbul. It sits right next to the North Anatolian Fault, which is one of the most active and well-studied strike-slip faults in the world, similar in many ways to the San Andreas. Since 1939, there's been a remarkable sequence of major earthquakes migrating westward along this fault, each one rupturing the next segment, like dominoes falling in slow motion over decades. The 1999 Izmit earthquake, magnitude 7.6, killed over 17,000 people about 60 miles east of Istanbul. Seismologists have been saying for years that the next major rupture is likely to be on the segment directly beneath the Sea of Marmara, right next to Istanbul, a city of over 15 million people. The probability estimates vary, but many studies put the chance of a magnitude 7 or greater earthquake near Istanbul within the next few decades at somewhere around 60 to 70%. Those are sobering numbers. And Istanbul knows this. The Turkish government knows this. There have been major initiatives, building surveys, retrofit programs, new construction codes modeled on the latest international standards. After 1999, there was real momentum. But Istanbul is also a city that grew explosively in the second half of the 20th century, with enormous amounts of informal and semi-formal construction that doesn't meet any code. Millions of people live in reinforced concrete apartment buildings that were built quickly and cheaply, often with insufficient steel reinforcement, often with that soft story problem on the ground floor. Retrofitting all of those buildings is a project of almost incomprehensible scale and cost. And so progress is slow. And the fault doesn't care about progress. The fault is accumulating strain right now, this moment, while you're lying here listening to this, and it will rupture when the stress exceeds the friction, and the buildings will either stand or they won't. Or think about Kathmandu in Nepal, which sits in a valley that's essentially a dried-up lakebed. Soft sediments that amplify seismic waves, exactly the kind of ground conditions that make earthquakes worse. The 2015 Gorkha earthquake, magnitude 7.8, killed nearly 9,000 people and destroyed or damaged over 800,000 structures. Many of the buildings that collapsed were unreinforced masonry, brick and stone with mud mortar, the kind of construction that's been used in the region for centuries and that has almost no resistance to lateral shaking. The earthquake was devastating, but seismologists pointed out something unsettling afterward. It wasn't actually the worst-case scenario. the rupture didn't extend as far as it could have. The shaking in Kathmandu, while severe, wasn't as intense as models suggested a closer or larger event could produce. In other words, the 2015 earthquake was bad, but the really big one on that fault system, the kind of event that historical records suggest has happened before, could be significantly worse. And the rebuilding after 2015 has been a slow, complicated process, hampered by political instability, limited resources, and the sheer difficulty of changing construction practices in a country where most buildings are built by their owners, not by professional contractors following engineered plans. Now contrast that with Chile. Chile is one of the most seismically active countries on Earth. It sits along the boundary where the Nazca Plate subducts beneath the South American plate, the same kind of convergent boundary that produces the world's largest earthquakes. Chile experienced the most powerful earthquake ever recorded, the 1960 Valdivia earthquake, magnitude 9.5, an almost incomprehensible release of energy. And Chile has responded to its seismic reality with some of the most stringent building codes in the world, rigorously enforced, continuously updated. When a magnitude 8.8 earthquake struck central Chile in February 2010, the sixth largest earthquake ever instrumentally recorded, the death toll was around 525. Which is tragic. Every one of those deaths is tragic, but for a magnitude 8.8 earthquake affecting a population of millions, that number reflects extraordinary engineering success. Buildings designed to Chilean codes generally performed as intended. The country's investment in earthquake-resistant construction, developed over decades and paid for by a society that takes seismic risk seriously because the earthquakes come often enough that people remember them, saved tens of thousands of lives that night. And that's a crucial insight, actually. Chile's success isn't just about engineering knowledge. It's about institutional memory. Chileans experience significant earthquakes frequently enough that the risk feels real, not abstract. The normalcy bias doesn't take hold the same way because the earthquakes keep reminding people every generation has its earthquake. Compare that with Cascadia, where the last great earthquake was in 1700, or with the New Madrid seismic zone in the central United States, where 3 massive earthquakes struck in the winter of 1811 to 1812, powerful enough to ring church bells in Boston, to make the Mississippi River appear to flow backward. But nothing comparable has happened since. 200 years of quiet. 200 years for cities like Memphis and St. Louis to grow up on top of that seismic zone, mostly without earthquake-resistant construction, because it just doesn't feel like earthquake country. So the question becomes, how do you motivate preparation for an event that's inevitable on geological timescales but unpredictable on human ones? How do you get a city council to spend $50 million retrofitting schools and bridges for an earthquake that might come tomorrow, or might come in 150 years? How do you get a homeowner to bolt their house to its foundation when the last significant earthquake in their area was before they were born? These aren't engineering problems. The engineering is solved. These are problems of psychology, of economics, of governance, of the stories we tell ourselves about what's likely to happen to us. And yet, slowly, imperfectly, progress does happen. It usually happens after a disaster, which is a terrible way to learn. But it's how humans have always learned about earthquakes. The 1906 San Francisco earthquake led to better fire codes and the beginning of seismic engineering research. The 1933 Long Beach earthquake led to the Field Act requiring earthquake-resistant school construction. The 1971 San Fernando earthquake revealed problems with freeway overpasses and hospital design. The 1994 Northridge earthquake exposed weaknesses in welded steel connections that nobody had anticipated. Each disaster teaches something, and the codes get updated, and the next generation of buildings is a little better. But there's another path, a harder path, which is learning from science rather than from catastrophe. And that's what places like the Pacific Northwest are trying to do right now with Cascadia. The science is clear. A great earthquake is coming. The fault is locked and loaded. The strain has been building for over 3 centuries. The question is whether the region can muster the political will and the economic investment to prepare before it happens rather than after. Oregon has begun requiring seismic retrofits for certain critical buildings. Washington has invested in early warning infrastructure. FEMA has conducted massive planning exercises. There was one called Cascadia Rising in 2016 that simulated a magnitude 9.0 earthquake and the resulting tsunami, and the results were sobering. The exercise projected tens of thousands of casualties, the destruction of critical infrastructure, highways and bridges severed, communities on the coast completely cut off, a recovery timeline measured in years. And this is where earthquake science in the 21st century finds itself. Not struggling with the physics anymore, not lacking the engineering solutions, but grappling with the profoundly human challenge of acting on what we know before the ground forces us to. It's a strange position. We can map the faults, measure the strain, estimate the probabilities, model the shaking, design the buildings. We can even, in some cases, give people a few seconds of warning. What we can't do, what no amount of science can do, is make the earth hold still. The plates are moving right now. They've been moving for billions of years. They'll keep moving long after every city we've ever built has crumbled to dust and been subducted back into the mantle. And somewhere along one of those boundaries, right now, stress is building on a locked fault, grain by grain, millimeter by millimeter, the rock bending like a bow being drawn back, storing elastic energy that will eventually be released in a few violent seconds that reshape everything above it. The question isn't whether. The question is only when, and whether we'll be ready, and what ready even means when you're talking about a force that can move mountains, literally move mountains, because that's what earthquakes do. They've pushed up the Himalayas, carved the Rift Valley, raised the Andes, and they'll keep doing it whether we're watching or not. So what does it mean to be ready for something like that? Maybe it starts with humility, with accepting that the earth isn't a stage we built our cities on. It's a living, shifting, restless thing, and we're just perched on top of it. Temporary tenants on a surface that's always in motion. Every building we construct, every bridge we span across a river, every tunnel we bore through a hillside. These are all negotiations with forces that are vastly, incomprehensibly larger than anything we can generate. And the fact that most of our structures stand up most of the time isn't a sign that we've conquered those forces. It's a sign that the forces haven't fully expressed themselves yet. Not in that particular spot, not during the lifetime of that particular building. But here's what I find quietly remarkable, and it's something worth sitting with as you settle in tonight. Despite all of that, despite the sheer asymmetry between tectonic forces and human engineering, we've gotten genuinely, impressively good at this. Not perfect, never perfect, but good. And the story of how we got good is really the story we've been tracing all evening, isn't it? From Zhang Heng's bronze vessel in 2nd century China, trying to figure out which direction the shaking came from, to Robert Mallet trudging across southern Italy cataloging destruction, to Alfred Wegener dying on a Greenland ice sheet with the right answer and no mechanism to prove it, to Marie Tharp painstakingly drawing the ocean floor and revealing the spine of a new theory to the engineers in Tokyo and Santiago and San Francisco who kept rebuilding, kept learning, kept refining their codes one disaster at a time. That arc, that long, slow, sometimes heartbreaking arc from ignorance to understanding, it's one of the most human stories there is, because it's not a story of genius striking like lightning. It's a story of accumulation, of paying attention, of looking at the rubble after a disaster and asking not just what happened, but why did this building fall and that one didn't? And then writing that answer into the next set of building codes and training the next generation of engineers, and slowly, incrementally, raising the standard of what we expect our structures to withstand. Think about what that means in practical terms. In 1906, when the San Andreas Fault ruptured beneath San Francisco, the city burned for 3 days. About 3,000 people died. The engineering profession barely had a vocabulary for seismic design. Fast forward to 1989, the Loma Prieta earthquake, also in the San Francisco Bay Area, magnitude 6.9. 63 people died. That's still 63 people too many, and each one of those deaths was a tragedy. But the difference between 3,000 and 63 in a region that had grown enormously in population, that difference is engineering. That difference is building codes. That difference is the accumulated knowledge of 83 years of studying earthquakes, testing materials, developing better designs, and having the institutional will to enforce them. Or think about Chile. We talked about Chile earlier, how their 2010 earthquake was magnitude 8.8, one of the most powerful earthquakes ever recorded, and yet the death toll was around 525. Compare that to Haiti's magnitude 7.0 earthquake just weeks earlier, which killed over 200,000 people. The Chilean earthquake released roughly 500 times more energy than Haiti's. 500 times. And yet the death toll was a fraction of a percent of Haiti's. That's not luck. That's not geography, though geography played a role. That's decades of institutional commitment to earthquake engineering, driven by the fact that Chile gets hit hard and often, and they decided, as a society, through their building codes and their engineering schools and their government regulations, that they were going to take it seriously. And that word, decided, is doing a lot of work in that sentence. Because that's really what it comes down to, isn't it? The science is there. The engineering solutions exist. Base isolation, moment-resisting frames, shear walls, energy-dissipating dampers, flexible connections, redundant load paths. We know how to build structures that can ride out severe shaking. We know how to design foundations that account for soil liquefaction. We know how to build tsunami walls and evacuation routes and early warning systems that give people those precious seconds to drop, cover, and hold on, or to start moving to higher ground. The knowledge exists. The question is always whether we choose to use it, and how broadly, and how consistently, and whether we keep choosing it year after year, decade after decade, even when the ground has been quiet and the memory of the last earthquake has faded, and the money could be spent on something with a more immediate payoff. That's the hard part. Not the physics, not the engineering. The sustained collective will to prepare for something that might not happen in your lifetime, or your children's lifetime, but that will happen eventually. And you know, there's something almost meditative about that idea, about the relationship between human time and geological time. We live in these brief windows, 70, 80, 90 years if we're lucky, and during those windows, the earth might shake beneath us once, or twice, or never. And it's natural, it's completely understandable to calibrate our sense of risk to our own experience. If you've never felt an earthquake, it's hard to feel urgency about one. If the last big one was before you were born, it starts to feel like history rather than prophecy. But the faults don't care about our timescales. The Cascadia subduction zone doesn't know that 325 years have passed since its last full rupture in January of 1700. It doesn't know that the cities of Portland and Seattle and Vancouver have grown up along its length. It only knows, if knows is even a word you can use for a geological process, that the Juan de Fuca plate is still pushing beneath the North American plate at about 40 millimeters a year, and that the interface between them is locked, and that strain is accumulating, and that at some point the accumulated stress will exceed the frictional strength of the fault, and the whole thing will let go. And when it does, the physics will be exactly the same physics that operated in 1700 and in 1500 before that, and in all the ruptures stretching back thousands of years that we can read in the geological record. The drowned forests, the tsunami sand layers, the suddenly subsided coastlines. The Earth has been rehearsing this, over and over. We're the ones who are new to the show. But, and here's what I want to leave you with because I think it matters, being new to the show doesn't mean being helpless. It means the opposite, actually, because we're the first species on this planet that can understand what's happening beneath our feet. We're the first ones who can read those tsunami sand layers and know what they mean. We're the first ones who can measure the strain on a locked fault with GPS satellites and calculate how much energy is stored there. We're the first ones who can design buildings that flex instead of break, who can create warning systems that outrun seismic waves, who can model the shaking before it happens and tell a city, with reasonable confidence, which neighborhoods will shake the hardest and which buildings are most likely to fail. That's extraordinary when you think about it. For most of human history, earthquakes were acts of gods, punishment, caprice, mystery. The ground shook, and you either survived or you didn't. And there was nothing you could do about it except pray and rebuild. And now, in the span of maybe 150 years, a geological instant, barely a heartbeat in the life of a tectonic plate, we've gone from that to understanding the mechanism so thoroughly that we can engineer our way toward survival. Not guaranteed survival, not invulnerability, but a dramatically better chance. Robert Mallet would be astonished. He spent years mapping the intensity of earthquake damage across southern Italy, trying to figure out the basic physics of how seismic waves travel through the ground. He had to set off explosions on beaches and time the waves with a pocket watch. And now, we have global seismic networks with thousands of stations, recording every tremor on the planet in real time, feeding data into models that can locate an earthquake's hypocenter within kilometers and calculate its magnitude within seconds. Marie Tharp would be astonished. She spent years hand-drawing profiles of the ocean floor from sonar data, and her colleagues initially dismissed her mid-ocean rift interpretation as girl talk. And now, we have satellite altimetry mapping the seafloor topography from space, and submersibles diving to the spreading ridges to watch new crust being born. Wegener would be astonished, and probably a little vindicated, and maybe a little sad, that it took 40 years after his death for the world to come around to what he'd been trying to tell them. The story of earthquake science is a story of people being right too early, of evidence being ignored because the mechanism wasn't clear, of disasters forcing reckonings that should have happened sooner. But it's also a story of progress, real, measurable, life-saving progress. Every earthquake that kills fewer people than the last comparable one in a comparable place, that's the proof. Every building that sways but doesn't fall, Every early warning alert that gives a school full of children time to get under their desks. Every retrofitted bridge that stays standing when the ground liquefies beneath its foundations. That's the accumulated inheritance of everyone who studied this problem, from the ancients who noticed that earthquakes cluster near certain coastlines, to the modern seismologists who can tell you why. And so tonight, as you're lying here, the Earth is doing what it always does. The plates are moving. Somewhere in the Pacific, the ring of fire is living up to its name. A volcano is venting. A subduction zone is straining. A transform fault is creeping. Somewhere in the mid-Atlantic, new crust is being born at the spreading ridge, hot basalt welling up from the mantle and cooling in the frigid water, pushing Europe and North America a few centimeters farther apart. Somewhere deep in the mantle, convection currents are churning, driven by the heat of radioactive decay and the residual warmth from the planet's formation 4.5 billion years ago. The same heat engine that's been driving plate tectonics for most of Earth's history. It's all happening right now, silently, for the most part, imperceptibly, from where you are. The ground beneath you feels solid and still, and for all practical purposes, tonight, it is. But it's moving. Everything is always moving. The continent you're lying on is drifting. The plates are shuffling. The faults are loading. And the whole restless, magnificent machine of the Earth's interior is turning over, cycling rock from surface to mantle and back again, in a process so slow that no human lifetime can witness more than the tiniest fraction of it. And there's something strangely comforting about that, I think. About knowing that the Earth is alive, not alive in the biological sense, but dynamic, active, always in process. The mountains outside your window, if you have mountains outside your window, aren't permanent fixtures. They're moments in a process. They were pushed up, and they're being worn down, and the material that erodes off them will eventually be carried to the sea and subducted back into the mantle and melted and erupted again somewhere else millions of years from now as part of a mountain range that doesn't exist yet, on a continent whose shape we can't predict. It's all one big cycle. Rock cycle, tectonic cycle, earthquake cycle. Stress builds, stress releases, the landscape changes, and then it starts again. And we're here for this tiny window of it, perched on our little patch of crust, building our cities and our bridges and our lives, doing our best to understand the forces beneath us and to build wisely on top of them. That's enough for tonight, I think. The plates will keep moving while you sleep. They don't need you to watch them. The faults will keep accumulating their patient strain, millimeter by millimeter, and the seismometers will keep their quiet vigil, recording every tiny tremor, adding to the vast library of data that helps us understand this restless planet a little better with each passing year. And tomorrow the Earth will still be here, solid under your feet, carrying you and everyone you love on its slow, ancient journey across the surface of a world that is never, ever quite as still as it seems. But tonight, you can be still. Let the Earth do its work. You've done yours. Rest now and sleep well.